Hi everyone. In this video I'm going to go over an analysis that was provided by Jupox in his text, Multilevel Analysis Techniques and Applications. So this set of analyses are actually coming from Chapter 2 where he performed multi-level regression analysis designed to predict students' self-rated popularity. So basically within those models, self-rated popularity was a level 1 outcome variable. The level 1 predictors were gender, which was coded 0 for male, 1 for female, and self-rated extroversion. The level 2 predictor in the model was a classroom level predictor, which was teacher experience. There were 2,000 students who were nested within 100 classrooms. So also consistent with the example, we're going to be using maximum likelihood estimation, and we're not going to be performing any type of centering in this demonstration. But he does cover centering in Chapter 4. So let me just note, too, that I will provide a link to the data and this PowerPoint underneath the video description. So the first model that Hawks presents is an intercept-only model. So you can see right here I've laid it out in two separate equations and then a combined model. So this first set of equations right here are just basically laying out the equations at level 1 and level 2. So the Yij is referring to student I in classroom J's popularity score. That is set equal to beta 0j, which is essentially going to be the classroom mean for that student, plus epsilon ij, which is the deviation of that student's score on Y and that student's classroom mean. At level 2, you can see that we have the classroom mean, which is the beta 0j, set equal to gamma 00, which is going to be the grand mean of all the classroom means, plus mu 0j, which is essentially going to be the deviation of that student's classroom mean from the grand mean. So when we, through substitution, what we end up with is this right here, where we're basically saying each student I in classroom J's popularity score is equal to the grand mean of the classroom means plus the classroom specific deviation from the grand mean plus that student's deviation from their classroom mean. So here I've opened up Jamovi, and you can see that we have a level 2 identifier. That's referring to the classroom identifier. You can also see that we have extroversion, sex right here, which we're just going to call gender identification or gender. Then also you can see that, I'll move this over, there's our popularity variable, which is a DV, and there's teacher experience. I know that these right here are already appearing as nominal variables. If we want to set these for continuous, we can do that very easily. There's the first one, and then for sex, if we wanted to leave it as nominal or continuous, since it's a binary variable, it's not really going to matter, but I'll go ahead and set it as continuous here. So then next what we'll do is we'll go to linear models and then go down to mixed model right here. So the first thing that we're going to do is specify that intercept-only model by moving our level 2 identifier variable down to the cluster variables box, and we're going to move our popular variable up to the dependent variable box. So next, going down to estimation, the default in Jamovi is REML, or restricted maximum likelihood, but to be consistent with the presentation, I'm going to click off of that so we get maximum likelihood estimates. We'll scroll down and then move under random components. We'll move intercept over to the box that says random components, and now you can see things start filling in. And then if I want a likelihood ratio test for the random effects, I can click on that as well. So looking at our output, you'll see first off some model fit information at the top, and you'll see that we have AIC and BIC and log likelihood, and these are three kind of approaches to evaluating the fit of your model, but these are not really useful for evaluating a single model. They're most useful when it comes to making model comparisons. So just looking at the numbers by themselves is not going to tell you very much about the fit of a specific model, but when you're comparing different models, that's where it's going to be most valuable. Just so you know, if you take the log likelihood and multiply by -2, that gets you an index that's referred to as the deviance. And basically, the deviance is most helpful when you're making comparisons between nested models. So basically, the difference in deviance would be distributed as a chi-square, and you could actually carry out a chi-square test of the difference in fit between nested models using the deviance value. But in general, if you have two deviances and you're comparing two different models, the model with the lower deviance is preferred. The AIC and BIC are two additional indices that are useful for model comparison, but in addition to comparing nested models, these are particularly useful when it comes to testing or comparing non-nested models. So in general, when you're comparing multiple non-nested models, models with the lower AIC or BIC values would be the preferred models in terms of overall fit. Down here, you'll see that we get, it says R-squared marginal and R-squared conditional. And these are actually not R-squares in the traditional sense that we're used to in the context of least squares regression. So it's actually better to think about these as pseudo R-squares. And the R-squared marginal is really referring to sort of a pseudo R-square when you are incorporating fixed effects within the model, which we don't have in this particular case in terms of predictors. The R-squared conditional is accounting for both fixed and random effects. So at any rate, you don't see those pseudo R-squares appearing in a lot of other programs, but they are appearing here, and I have some reference material in the PowerPoint if you want to read up a little bit more on those. So down here under fixed effects parameter estimates, we have our gamma 00, which is our intercept. And so essentially in this context, because we don't have any predictors at level 1, we can just interpret this as essentially the average of the classroom means with respect to popularity. There is a significance test that is provided if you wanted to test whether that's significantly different from 0, but oftentimes it's not particularly helpful, and so more often than not, I don't do anything, or most folks will not be doing anything with testing whether the intercept is significantly different from 0. Down below, we've got our random components, so we have the variance estimates for the random intercept. So there's the variance estimate right there. If you want it in terms of standard deviation, there it is right there. The variance estimate for the level 1 residuals is 1.222. The standard deviation of those would be 1.105. And then over here is the intra-class correlation coefficient, which is helpful for determining whether or not it's even appropriate to be performing multi-level analysis. So the basic idea with multi-level analysis, one of the key reasons why we perform it is because we are wanting to take into account clustering of observations within groups. And so what happens is that either through natural clustering or through some type of sampling approach that results in clustering of observations, what that yields is dependence within the groups in terms of your DV. And so individuals within groups become more similar than they are between. So the ICC, or the interclass correlation coefficient, is used to sort of evaluate the presence of clustering. And when there is the presence of clustering in the data, then that can bias your standard errors and perhaps your parameter estimates as well. So at any rate, the ICC is just computed as a ratio of the variance to the sum of the variance of the intercepts to the variance of the residuals. So basically, if I was to kind of use some notation that I use in my PowerPoint, I would just write this out as the variance of mu 0j, which is the variance of the intercepts, divided by the variance of the intercepts, I'll just say mu 0j again, plus the variance of the level 1 residuals, which is epsilon ij right here. So it's just that ratio. And so basically an ICC of 0 would be consistent with simple random sampling, and there's not really much concern about clustering effects in your data. But as you have values that are greater than 0, then you have greater concern with clustering. And so values that are 0.05 or below might be considered lower levels, are indicative of lower levels of clustering, but that can still have ramifications when it comes to your interpretation. So you can see right here the ICC is 0.362, which is pretty substantial. Down here, random effect LRT, this is a likelihood ratio test. And so this is effectively testing this variance component for the intercept. So it's basically testing this variance right here. And the null hypothesis is that the variance is equal to 0. So if this is significant, as it is right here, then it's indicating that there's significant variability across our level 2 units, in this case our classrooms, with respect to popularity. And that would be another indicator of evidence of significant clustering going on. Now, the next model that Hawks tested was one in which he included level 1 and level 2 predictors in the model, and he also allowed the random effects to covary. So looking at our level 1 equation, you can see right here that each person I in classroom J, their score with respect to popularity is a function of the classroom intercept right here, which is the beta 0J. So the intercept is just basically the classroom mean adjusted for the predictors in the model. So you could think about it as a conditional mean. Then you've got plus beta 1J times our gender variable, plus beta 2J times extroversion, plus residual error at level 1. So the level 2 equations now, you can see that we have beta 0J for our intercept. And in this case, previously we had is equal to gamma 00 plus mu 0J. And now we're adding in a predictor of the variation in the classroom intercepts. And that predictor is teacher experience. So the gamma 01 right here is essentially our is the regression slope associated with teacher experience that's which is being used as a predictor of the variation in the intercepts. Now you also see beta 1J right here is equal to gamma 10, and that is basically the fixed slope for gender. So in other words, if we compute the slope for gender across all the classroom and average them out, we get a grand mean with respect to the slope for gender. And then this right here would be the classroom deviation from the grand mean with respect to the slope. That's the mu 1J that you see here. So basically, if we did not include the mu 1J, then we would just be treating the slope for gender as fixed. But in this case, we have both a fixed and a random component with respect to gender. The same goes with respect to beta 2J, which is this is the grand mean of the intercept slope across all of the classrooms, plus the random component, which is the deviation of a classroom slope for extroversion from the grand mean of the classroom slopes. So through substitution, we end up with this combined model right here. So it's a lot to look at, but that's basically our model. So let's go ahead and run the analysis. So now we're back into Jamovi, and I'm going to scroll up. So now I'm going to move, I'll move sex over to the covariance box. It's like I said, it's a binary variable, so we can treat it as a covariate, and it really wouldn't have made any difference in this case if we had left it as nominal or scale as we're doing right here. Where things do matter in terms of categorical predictors is when you have 3 or more levels, then you would definitely be wanting to include those in the factors box above. So I'm now going to move extroversion down to the covariance box and teacher experience down to the covariance box as well. Now, as I'm adding these in, let me just note, too, that by default, the program, under covariate scaling, you can see that the program defaults by centering these variables at the grand mean. And when you click on this box, you can see that there are various options in terms of centering. But like I said, for the presentation in Chapter 2, there's no centering. So I'm going to set all of these to none so that we can remain consistent with the output that's presented in that chapter. Now, another thing that we want to do is go back under random effects and move sex over, because we're going to allow that slope to randomly vary, and extroversions. We're going to move that over as well. And when we do this, what you'll see is that we get an error message. So it says up here, model failed to converge, results may be uninterpretable or misleading. Try to refine your model. And one of the reasons why, or the main reason why, is as we scroll down and we start looking at the random components right here, you can see that the variance estimate for sex, the slope, is essentially 0. It's very, very close to 0. And essentially what that means is that the slope variance, because it's 0, it really should be treated as fixed. And it's creating a problem with respect to our model convergence. So what we're going to do is remove that random effect. And let me also note, too, that by default, when you're adding in multiple random effects, like when you have the random effect for the intercept and any slopes, by default, the program sets it up to where those random effects are correlated. So if you didn't want them to be correlated, we would click on the not correlated box. But again, using the example that's provided in Chapter 2, they actually allowed the random effects to correlate. And so before I actually move on and remove that slope random effect, I do want to mention down here under random components, you'll see that we have, it says intercept, sex, and extroversion. So we have variance estimates for all three of those right here, as well as the level 1 residual variance right here. You also see down here, because this is clicked as correlated, this is the correlation. The first one is the correlation between intercept variance, the intercept, random intercepts, and random sex slopes right there. Next, we have the intercepts and extroversion slopes. That's the correlation. And then we have sex and extroversion. That's the correlation between the random slopes. So at any rate, what we're going to do is go ahead and remove the random effect for sex. So I'm going to move this one out, put it back over here. And so now when we estimate the model, this is what it looks like. You can see we don't have an error message that's involved. So as you scroll down, you can see first off under fixed effects parameter estimates, sex, we have a positive coefficient value. So if you think about the coding or remember the coding, it was coded 0 for male, 1 for female. So the fact that this coefficient is positive is indicating that females scored higher than males, basically 1.25 points on average higher on popularity than males did. And you can see that that coefficient was significant. Then we have extroversion, and we have the regression coefficient here for that level 1 predictor, and it's statistically significant. So this is indicating that students who scored higher with respect to extroversion were predicted to score higher with respect to popularity. And then you also have the level 2 predictor right here, teacher experience. And basically, the relationship between teacher experience and popularity is kind of flowing through that random variation in the intercepts. So you can see that we have a positive coefficient right here. Basically, this level 2 predictor is a positive predictor of essentially popularity, or more specifically, the classroom means with respect to popularity. And so you can see it's significant. So basically, teachers with more experience were predicted to have classrooms that had greater mean levels of popularity. So then next you can see that we have our random components. Again, there's our variance estimates for the intercept and extroversion right there. So those are level 2 variance estimates. Then we have the level 1 residual variance. You actually see that the ICC has increased relative to that intercept-only model. So then down here, the correlation between the random intercept and slope, you can see right here it's negative 0.886. So it's very highly correlated in this case. So now we want to see if we can model a level 2 predictor of the variation in the slopes associated with extroversion. So the only level 2 predictor that we have available in our data set happens to be teacher experience. So we're now going to model teacher experience as a predictor of the variation in classroom slopes for extroversion. So in this case, we have our level 1 equation. You can see it looks pretty much the same way that we had before. Our level 2 equations, we have, again, teacher experience serving as a predictor of the variation in classroom intercepts. Here we have our fixed effect with respect to gender. So this is treating the effect of gender to be the same across classrooms. And the reason why is because we don't have that mu1j that we had previously. So we had fixed that the variance of the slopes for gender to 0 essentially. And then for beta 2j right here, you can see once again we have the gamma 2 0. That's the grand mean of the slopes for extroversion. There's our plus 2j right there, so we are capturing variation in those slopes across classrooms. But now we're adding in the predictor teacher experience. So you can see right here that we have a the gamma 2,1 is referring to the regression coefficient there. And so through substitution down here in the combined model, you can see that the gamma 2,1 is essentially capturing is the regression slope for the cross-level interaction between teacher experience and extroversion. So this is at level 2, the teacher experience, and level 1 is the extroversion that we see right there. So going back up here, you can see we basically have everything specified as we need to in the first set of boxes, but now we're going to go down to fixed effects box right here. And what I'm going to do is I'm going to highlight teacher experience and then extroversion right here, and then click on this arrow and then click interaction. So this is going to create an interaction term for our regression model. And so now, as we kind of scroll down here, you can see that we have our interaction term. That's the regression slope. It's negative, and you can see it's statistically significant. So you can already see, too, that if we look at extroversion by itself, you can see there's a positive regression slope, and it was significant. However, what this basically, the interaction term is conditioning that relationship. So what this means is that for every 1 unit increase that we have in terms of teacher experience, the slope for extroversion is actually decreasing by 0.0247. So the slope is changing as a function of the classroom level teacher experience variable. Now, if we want to scroll down a little bit further, we can kind of probe the interaction by doing the following. So under plots, we can move extroversion over to the horizontal axis box and teacher experience to the separate lines box right there. And you can see down below that we have a plot, our effects plots right there. And you can see that we have plots of the relationship between extroversion and popularity at 3 different levels of teacher experience. So this is at 1 standard deviation below the mean with respect to teacher experience, right at the mean on teacher experience, and then plus 1 standard deviations from the mean on teacher experience. So these are just essentially three arbitrary points along the distribution for teacher experience, but we could think about them loosely as sort of low, medium, and high, if you will. So you can see the orange line right here, which is at high teacher experience. That slope is much less pronounced than the slope at low teacher experience that we see right here. Now, if we want to test those slopes out, we can go down a little bit further under Simple Effects box, and I'll move extroversion to the Simple Effects variable box and then teacher experience to the moderator box. And so now, as we're looking at this, you can see it's busy figuring right now, but you can see underneath that it's got simple effects of extroversion. So these estimates here, these are the regression slopes that essentially we have in the figure below. So if I kind of scroll up a little bit, make it a little easier to see, you can see that at mean minus 1 standard deviation in terms of teacher experience, the slope is 0.613. So this blue line basically has a slope of 0.613, and you can see that it is statistically significant. Then at the mean, which is sort of the gray line, the slope is 0.451. You can see that it is also significant. And then the blue line, which is the orange line, which is the 0.289 right here. That's essentially the orange line reflecting teachers with the greatest or with higher levels of experience. that slope is also significant. But nevertheless, you can see visually right here, and also by just kind of comparing these slopes right here, that the slopes are differing. And that's what I mean when I say that the effect of extroversion on popularity is conditioned on the level of teacher expertise for a given student's class. So that is a basic rundown of much of the demonstrations that are provided in Chapter 2 of Hawkes's book. So I appreciate you watching.